Today I'll be talking about Kumozu, which is a tensor library and deep learning framework that I wrote in C++. So just as an introduction, a little background about me. I got my PhD in 2005 from UC Berkeley, and before joining PFN, I first worked at a small company, that AMG, which was acquired by Macrovision, and then they changed their name to Robi. I was there about 4.5 years, and then I spent about 5 years at Intel Corporation and joined PFN in April of this year. And a couple of recent projects, public projects, are that I'm a member of the Chainer development team, so which is another deep learning framework. But today I'm going to talk about a framework that I wrote in my spare time, Kumozu. And for my interest, interested in deep learning frameworks, matrix factorization, audio signal processing. My hobbies are music related. I play piano, also enjoy coffee roasting. So yeah, I'm going to talk about Kumozu today. The name is kind of arbitrary. As you can see here, it's actually a location in Miyaken. I chose the name because when I Googled it, nothing came up, so I thought it was safe. And I also did a lot of the coding when I spent vacation time in that area also. So I wrote much of Kumozu when I was in Kumozu. So here's the GitHub project page. And yeah, so I'll start just by giving an overview. Kumozu is some C++ software that I originally wrote just for personal research projects. And I eventually, the code got to the point where I thought some parts of it might be useful to maybe other researchers, so I released it on GitHub. So it currently contains a multi-dimensional matrix or tensor library and some plotting functions using GNU Plot's C++ API, as well as a library of utility functions and various deep learning functions that are optimized for CPU, and also contains some implementations of non-negative matrix factorization algorithms, which was originally what I wrote this code for, was to experiment with extensions of non-negative matrix factorization. And one of the most recent things I added to it was a layer to support deep learning frameworks, computation graphs. Since there are currently a large number of deep learning frameworks, I think I should maybe try to explain what Kumozu tries to be, or how it would be differentiated from the other frameworks. So it's intended to be used just as an easy to use deep learning framework for reasonable performance, for fast prototyping, and to support deployment of models to small devices. So it's written in C++ to have as broad a platform support as possible. I actually try to use C++ as for prototyping purposes. And there are some researchers and engineers that they prefer to use modern C++. And I'm not aware of other frameworks that are really written in a modern C++ style. And the focus is on fast prototyping and what I would call like early stage prototyping, which means it's models that are more experimental. Maybe one might consider trying to use something other than backpropagation to train a neural network, or something that maybe doesn't really fit well into some of the existing deep learning frameworks. So like very experimental models where the goal is just to get an implementation that's fast, but it doesn't need to be as fast as possible. It just needs to be fast enough to evaluate that model. So it's not intended to compete like at the high end. I think it'd be better to use for that kind of prototyping, maybe an existing framework that's already GPU optimized would be better. But say if one would like to implement some features that maybe they're not already implemented as functions or layers in another framework, and it would require writing some optimized C or C++ or CUDA code. If the model contains a lot of that kind of code, then that's what I was intending this framework to be useful for. And to support that, there's a focus on keeping the API and the software architecture as simple as possible, as simple as we can have it be, that still has good performance or makes efficient use of the hardware. And it's currently, I think, fairly well optimized for CPU, using OpenMP and I'd say an optimized BLAS library. And so there's currently no GPU support to maintain the other focus that I think it would introduce a lot of complexity. And since I'm the only developer, my priority when I can devote time to this is on adding new functionality rather than making it super optimized. And another thing that's maybe a little bit different about this framework is that, well, it uses a explicit data flow representation for computation graphs that other frameworks like TensorFlow, for example, use. But the way that the graph is specified is a bit different. I actually found it intuitive to use named ports for the nodes in the graph, as opposed to, say, ports that are indexed using an integer positional index. I found named ports more intuitive, so I use that. But other than that, maybe it's somewhat similar in the way the graph is specified. And here's just a quick list of some of what it is currently implemented. So it currently supports layer types such as convolution and batch normalization, dropout, things that are probably in most or all deep learning frameworks. Supports RNNs, and the computation graph is cheap to specify, or it's at runtime it's cheap to change the graph, and this also has I guess a chainer would call this parameter shape placeholder that's useful for convolutional networks, and basically figuring out the parameter sizes at runtime during the first forward data pass. So yeah, now I'll just talk about the architecture of this and how the computation graphs are specified. So the way that this works is, well, the computation graph is a directed graph, and it can be there's basically two types of nodes. There's an atomic node, and then there's a composite node, which is a container of other composite nodes or atomic nodes. So for those of you who are familiar with chainer, you could think of an atomic node as being like a link, and then a composite node as being like a chain. And both of these node types contain ports, which is how they receive input or produce output activations. And the ports have names, and each port is associated with a data tensor and a gradient tensor. And in this figure, the green is the data tensor, which I call a forward activation, and the red is the gradient tensor, which I call the backward activation. So, and just already said this. And okay, that's not important. And I also have there's a layer. In Kumozu, a layer just means it's a specific type of node that has just one input port and one output port. So layers in say a feed-forward network, like a convolutional network, they would actually be a subclass of layer in Kumozu. And to create a new node, say if one would like to implement a new kind of activation function or some kind of layer or node in some kind of experimental neural network, at minimum, that only requires just subclassing the node class and overriding two functions to specify the forward and the backward computations. That would be needed to create an atomic node, but to create a composite node, which is a container of other nodes, it basically just amounts to, again, creating a subclass of node and just placing other nodes inside it and then connecting the ports up to create the graph. And there's an API in the node class to support that. So constructing models with this framework, it's somewhat verbose because it requires explicitly connecting up ports from one node to another. But I think it's also intuitive because this is often it directly translates to, say, a type of network in a figure, such as, say, for a recurrent neural network. For papers that show figures of the network, it's typically shown as a data flow graph. So to implement that in Kumozu, one would just directly create the nodes and connect up the ports as they are in the figure. And maybe I should also mention that how this is, in the implementation of this, there's actually no data copying. Say if data is produced by that port C, and then consumed by the next node at port D, we don't explicitly copy data at runtime. Rather, the way this works is that we just pass a reference, which you can think of as a pointer, when at the time the graph is constructed, so that the internal node that reads from port D already has a pointer to the output activations of the node that produced the output for port C. So that makes it memory efficient and also results in so that there's no dynamic memory allocation unless the computation graph is changed at runtime. I think yes, I should also mention that how parameters work. So similar to forward and backward activations, we also have forward parameters and backward parameters, where forward parameters are the actual parameters or the weights, and then the backward parameters are gradients. So I might actually change the name of that, backward parameters, since it's not actually parameters. That might change in the future. And okay, so this is basically just concludes the summary of basically how the computation graphs work at a high level in Kumozu. So now I'd just like to move on to the underlying tensor library. So I wrote a tensor library from scratch rather than using an existing one, but it has similar features. In fact, some of the as other tensor libraries. In fact, some of the design was influenced a bit by the Torch 7 tensor library. So the one that I wrote, it currently supports up to 6-dimensional matrices. And one of the kind of unique features of this tensor library is the way that the utility functions work, in that to make memory, to avoid unnecessary or redundant dynamic memory allocations, most of the tensor utility functions typically do not return anything. They actually take both the input and the output tensors as references, and then the output tensor is resized if necessary. So I'll show an example of that later. I just found this feature. I designed it this way because I just found it. I liked it. It seemed kind of intuitive, and it was also memory efficient. The alternative would be say returning, like allocating a new array, which is typically when, say in Python, when one uses NumPy, that's a common way that NumPy is used. There's often a memory allocation when calling out a memory ufunc, or if we use the out parameter in NumPy, then that requires that the output array needs to already be sized to the correct shape. Otherwise, it won't work. Whereas in the one that I wrote here, most of the functions are such that you can actually pass in an output array that has the wrong size or has size 0, and it will just reshape it if necessary. So the programmer doesn't need to worry about that. So I'll just now go quickly through a few examples. Here, a matrix F just means a matrix of float data type. So we can create, say, a 0 matrix and then fill it with values using a function that, for those of you familiar with Torch, this is just like the Torch sequential function. It takes a closure to assign values to the elements of the array. And once we have that, we can say, now that I wrote a parallel version of the apply function. Say, so if we want to apply an element-wise function to the matrix, that's straightforward. Again, this is works the same way it works with C++, maybe well, analogously to the way it works in Torch in Lua. Now, as another example, let's suppose we'll start by creating a matrix and fill it with values. And this this illustrates a map function. This just shows how using the C++ 11 lambda functions or closures, how it's easy to write, say, a multi-threaded element-wise kernel that's fast and memory efficient using this kind of API. At least I find this useful. But I borrowed this idea from Torch. So this is, again, can also be done in Torch. But I wanted to use C++, so I wrote some of the same functionality in C++. And likewise, we have the narrow function from Torch, and reverse narrow, which does that, and various other utility functions such as generating random, various kinds of random data, and so I won't go over the whole utility library, but this is just a few examples to sort of get a feel for how it is to use it. Now, and the last example is just for matrix multiplication. So this is an example where we can, suppose we create the two input matrices, like a 3x4 and a 4x5, and then we multiply them, so the output should be 3x5. But we will actually take the output matrix C, and we're not going to set it to the correct size. We're actually just going to leave it. By default, it's initialized to size 0 with no dimensions. And we just pass a reference into the matrix multiply function, and the matrix multiply function will resize it. So many of the utility functions work like this. They take a reference as input, and they check the size, and if the size is not what it should be, it will be resized. So this way, if this is called in a loop, we can avoid unnecessary allocations, memory allocations. And this assumes that the check of the size is actually cheaper than allocating the new array, which I think it should be if we're dealing with large enough arrays. And this is convenient for the programmer because the programmer doesn't need to figure out what the output size should be in order to write memory efficient code. Okay, so that's it for the tensor examples. Now I'll just briefly go through some plotting examples. And basically all I did here was just write some wrappers around the GNU plot C++ API that support the tensor library data types. So the first example is actually just using an STL vector, so maybe that's not as interesting. But say here, if we'd like to do an image plot, say this matrix could represent, like if we're using a neural network that generates either weights or filters that we'd like to visualize, or working with actual images, then these kinds of plotting utilities are useful. So we can do a grayscale plot, or say an RGB plot. So here I just create a three-dimensional tensor, and then fill it with values, and we can plot that. And I just have some images of the kinds of plots that we created here. So basically, at this point, the combination of the tensor library and the plotting just means that we have something that's sort of equivalent to some of what one could do, say, if you're used to using NumPy and Matplotlib in Python. It's actually possible to do some of that in C++ if you really want to use C++. That was sort of the intention here, to be able to use C++ as for prototyping array-based stuff. And by using C++, the language doesn't get in the way of the performance like it does often with Python. So say I can write loops that operate like element-wise on these arrays, and it's still going to run fast. And it's really easy to use, almost trivial often, to use OpenMP to parallelize it, so we can get very efficient multi-threaded code with really not much more verbose code than there would be doing the same thing in Python. Although in other cases, C++ can be much more verbose than Python, so there is a trade-off there. Okay, so now I'll just move on. I'll just go very quickly through these examples. This is just like, I'm just going to quickly cover some of the current examples in Kumozu, but I won't go into a lot of detail on them. But you can check out the GitHub page if you're interested. So I've implemented the same network that was in a Torch blog, I think about a year or so ago, using Cypher 10. So I have a convolutional BGG style network. And just as a performance comparison, I think on my just on a one of the fastest Core i7 desktop CPUs, I think it took about 24 hours. We ran the Torch, the equivalent Torch model on a GTX 1070, and I think it took me somewhere between 5 and 10 hours. I don't know exactly, but so of course the GPU was several times faster. But coding this in C++ was also a lot less work than, say, optimizing for GPU. Although if you'd like to use convolutional networks only, then it may be a better choice to use another framework that already is optimized for GPU. So I guess I'll skip over the, but this is interesting. So this is an example of using the plotting functions that I wrote. So one of the things I'd like to do in prototyping, or when I'm implementing something, I like to visualize it for debugging and also just to get a feel for what it's doing. So using these plotting functions, I can actually update them, say, live, so that say every iteration or at some point I can redraw the plot in the same figure. So in a training loop, say if I'm training the network, if you run one of the Cypher 10 example in Kumozu, after each epoch, it will actually refresh a plot with a different random input test or validation image, and it will plot the filters or the weights of all of the layers, and also the output. So the output there, I think there are 10 classes, so there's a white bar, which hopefully is for the dog class. This is just a feature that I think is, I like to be able to look at stuff as it's training. So using the plotting utilities, it already has enough functionality to support that. Although writing the code to create this figure is a bit verbose. And likewise, like, the plots of the training error or loss, they can be updated, say every iteration or epoch easily as well. And I also have an MNIST example, so it's the same thing. And then the last neural network example in Kumozu is I've implemented what supports RNNs. So yeah, maybe before I get to the example, I'll just briefly explain how RNNs are created. The way that this is typically that one would create an RNN in Kumozu is to first specify subgraph that represents a single time slice, or maybe even before that, like if we have a multi-layer, say a multi-layer LSTM, we might have a composite node that represents one LSTM node, and then create another composite node for one time slice that contains everything just in one time slice, and then we will pass that to a class that performs automatic slice unrolling, so that we can perform truncated back propagation through time. So maybe there's not enough time to go through the code, but this is just what the code would look like, say, to create a simple RNN node. So we use subclass node and specify the ports and the nodes and how they're connected together. And I can use any names I want for the ports. So I can actually say if I could use H or Y or yeah, it's just a string. The name's just a string, so it's anything I would like. So it's actually not a lot of code to specify this. And I maybe should also mention that, well, you may notice that so far I think in none of my slides has there been a raw pointer. So I actually tried to avoid raw pointers that own memory like as much as possible in this framework. So that way I just rely on the underlying, say, STL vector class for all of the memory management, or most of the memory management. So actually, when we unroll this into like several time slices, then I use smart pointers for that. So actually, there is some dynamic memory allocation, but I really try to avoid it in this framework. So the way that you would create a recurrent neural network is, yeah, to use a slice unroller, and provided that certain functions are implemented, then this can be pretty automatic. But maybe I don't have enough time to explain it in detail. But conceptually, it's, yeah, you specify the graph for one time slice and then pass that into a slice unroller class that unrolls it as many time slices as one would like. And I currently have an example that of a character level language model using an LSTM that's the same as it's essentially the same network as the one that Karpathy used in his implemented in Torch in his blog, and this is just an example of the kind of output that it would produce. Here I trained it on War and Peace. So and this I believe took a few hours on CPU. So even though this is it's not using GPU, it's still possible to create networks, say, that operate on data sets, say, roughly the size of, say, something like Cipher10, or a long novel, or several tens of megabytes of text data, and to train recurrent neural network language models on them and run them on the CPU in just, say, hours to maybe a day. So for small models or relatively small data sets, even using CPU, it's possible to do some interesting prototyping with this. And finally, this was the original feature in it before I added the deep learning support, was actually for matrix factorization. Although most of the matrix factorization code is not currently public, but I hope to eventually put more of it on GitHub. But I currently, the public version currently does have just a implementations of, I believe, the Lee and Sung multiplicative NMF update algorithms, and then this is just another figure using the plotting functions that I wrote. So it's for these kinds of models, I like looking at them as they're training. It kind of looks, I think it looks cool to see how you can start with random, say W and H matrices, and given the input, watch as they converge to something. Yeah, so this also supports NMF and some extensions of NMF. And yeah, I think that's about it. So for the summary, for the current status, I would say that the current API is still very experimental. So I don't currently make any attempt for backward compatibility, but I'm actually not aware of any users of this. I use it, and it's on GitHub, but it's since there aren't really there isn't really a user base for this, I think it's fine to change the API whenever I feel like it for now. But hopefully it will become stable at some point if development continues on this. And the current layers and nodes that are implemented are already fairly well optimized for multi-core CPU. However, the data flow scheduler it's usable, but it requires that the user explicitly call a function when they add a new node that should not actually be needed. So that's something that I hope to make completely automated at some point. And also the code on GitHub is a little bit outdated. I don't update it that frequently, but I have updated the code base quite a bit since the last GitHub commit. So hopefully I'll update that soon. And finally, just some ideas for, say, some future work that might be interesting with this. I think one of the maybe things I would most like to try would be incorporating some chainer features into it, such as the define by run, because that can really make it a lot more intuitive to create the networks. I think that should be possible in C++, as well as other features from trainer, like it's a the trainer class in chainer. It could be interesting to try to incorporate some of that functionality in C++, and also say functionality like the dataset iterators from chainer. And on the for the data flow graphs, yeah, I think I mentioned the scheduler improvements. In fact, one of the nice features of representing a computation graph explicitly as a data flow graph is then that the user doesn't need to be concerned with the scheduling algorithm. So that means there could be a whole line of research involved in exploring different types of scheduling, distributed scheduling for, say, multi-machines, or just different types of static scheduling algorithms. So that's all possible. And I'm also considering maybe separating the tensor library from the framework, and just various API refactoring. And yeah, so I think that concludes the talk. So are there any questions?
This has support for multi-core computation.
Yes.
How does this scale to the number of top cores?
Currently, the bottlenecks in the networks that I've implemented, I think, are mainly in the layers that perform the matrix multiplications, like the linear layer and the convolutional layers. And the current implementation actually uses the SGEM, matrix multiply function from, say, an optimized BLAST library. So the scaling would be whatever it is in that how it is in the library. This would probably scale similarly. But for other types of networks, it could vary because some of the layers are better optimized than others, and I haven't performed really any empirical tests to observe how scaling is versus number of cores. I think that could be interesting, but yeah, for networks that are not bottlenecked by the matrix multiply function, I guess I don't have an answer. but most of the functions are at least multi-threaded using OpenMP. But perhaps they're not currently optimized for any particular CPU architecture. I'm currently not using OpenMP for features like there's SIMD, pragmas, and things like that, and I'm not currently using any of that. So just basically parallel for pragmas to parallelize most of the loops. Any other questions? Okay, so then yeah, thank you, everyone.